All right, everybody have a handout for today? Okay. We'll talk about the ID badges for Georgia tomorrow. All right, probability. Okay, so you don't have to write anything on this slide down. We'll give you examples of each of these things on your next slide in a second. So probability, you guys did probably basic probability in previous math classes. It calculates, estimates, or simulates the likelihood of a given event of happening. Okay, so it's our chances of a certain event happening. The probability experiment is what we actually do. So a probability experiment could be like rolling a die. An outcome are the different things that can occur when you do that experiment. So outcomes on rolling a die could be rolling a 1 or rolling a 4. Sample space is the set of all possible outcomes. So back to rolling a die, my set of all possible outcomes could be a 1, 2, 3, 4, 5, or 6. Those are the different things that happen when I roll a 6-sided die. And then we have also an event. So an event could be one of those outcomes, but it could be more than one. And that's where probability starts to get a little more complicated. We might calculate the probability of rolling a 2 and then rolling a 4 right after that. Okay, so that's more than one outcome combined to make an event. All right, so your first slide on your paper is this example. It says identify the sample space for this probability experiment. So a survey is the experiment. It consists of asking people for their blood types, which are O, A, B, or AB, and then including whether they're Rh positive or Rh negative. So that Rh factor is what makes your blood type A positive or B negative. That's that little positive negative thing we're talking about. So we want to figure out how many outcomes there are and identify the sample space. I'm going to do this with a tree diagram. We're not going to make very many tree diagrams because they're kind of tedious, but it's a good way to just kind of like organize the information we have. So I'm going to start first with what my Rh factor could be. So it could be positive or it could be negative. And then within each of those categories, I could have one of 4 blood types. So I could be O, A, B, or AB. O, A, B, or AB. Okay. So how many total outcomes are there? How many different blood types are there? There are 8. Okay, so that's how many little branches I end up with at the end if we have one of these tree diagrams. Okay, and the sample space, how we would list that is usually we make a little set bracket, little squiggly bracket, and then we list all of the possibilities. So O positive, A positive, B positive, A, B positive, and then all the negatives. O negative, A negative, B negative, A, B negative. Okay. So outcomes are the different answers people could give. Sample space is the set of all of those. And then an example of an event, I'll just put one on here so you have it in your notes, is if I survey 2 people, both of them have type A blood. Okay, so they could both be A positive or they could both be A negative, or one could be positive, one could be negative. And then that's something that we'll talk about how to calculate the probability of later on. Any questions on any of those terms? Oh, thank you. All right. Next slide. An example of a simple event. A simple event is an event that consists of a single outcome. So only one thing happens. So if I survey one person and they tell me their blood type is O positive, that's an example of a simple event. Only one outcome is included. So down here, we're trying to figure out how many outcomes there are in the event that's described. And if there's one event, we're going to label it as simple. And if there's more than one outcome, I should say, we're going to label it as not simple. Okay, so first one says, for quality control, you randomly select a machine part from a batch that has been manufactured that day. Okay, now what we want to focus on is the event itself. We want to know how many outcomes are within that event. In that event, we are selecting a specific defective machine part. Okay, so it might be like a defective belt, maybe, is what we're looking for in the machine. So that is one outcome only. One thing is happening. Okay, one outcome. It either happens, we select that specific machine part, or we don't. And therefore, it is an example of a simple event. Okay. Number 2, you roll a 6-sided die. Event B is rolling at least a 4. So if I roll at least a 4, what are ways for that to happen? I could roll what? Yeah, hold on. Hello, this is Miss McDonald. Hey, good, how are you? Yeah, he just actually came up here with a class, with a task for Jane. Oh, okay. Got it. Okay. Sending him down. Yes. Okay, bye. For you, sir. Head on back down. Okay, so if I roll one die, what are ways that I could get at least a 4? Yep. Yep, if I roll a 4, 5, or 6, so how many outcomes is that? 3 outcomes. And therefore, it is not simple. Okay? Any questions on what makes a simple event? Easy enough. All right, next. Again, something that you might remember from previous math classes. This is called the fundamental accounting principle. It's a way to figure out how events can happen in succession, happening with one another. So let's pretend I have one event that can happen in m different ways and another event that can happen in n different ways. The way they can happen concurrently is I multiply those numbers together, m times n. So when you did these, probably in middle school, you probably did a lot of problems with like restaurant menus. Like I have this many appetizers and I have this many entrees and I have this many desserts. How many ways can I order off the menu if I pick one from each column? Or I have this many shirts and this many pairs of pants and this many shoes. How many outfits can I make from my selections if I pick one of each? Okay, so that's this type of problem. So the example here says we're making a new car. We've got different manufacturer options, different car size options, and then different colors. We want to know how many different ways can the car be made. So from each category, we just pick how many selections we have. From the manufacturer, I have 3 choices. From the car size, I have 2 choices. And the color, I have 4 choices. So the number of choice in each category, that's the m and n that the formula is talking about. We just multiply them. 3 times 2 times 4, and we get 24 different ways the car that can be made. This saves us from having to make the big tree branches all the time. If we look back at that blood example, we had 2 different RH factors, right? Positive and negative. We had 4 different blood types, O, A, B, and AB. And if we multiply 2 times 4, that's where the 8 outcomes came from. So we can save ourselves time drawing all those graphics and just using this counting principle instead. Okay, so put that little paper aside. We're going to come back to it. We're going to do a little group activity here using the fundamental accounting principle. So I need you to get to groups of either 3 or 4. You can pick who you want to work with. I don't care. And I want you to work through these problems. Okay? When it says that you don't have to choose something, that's a choice. Okay? You'll know what I mean when you read it. It says you don't have to pick something, that's a choice. Yes. Okay, so we're going to Dunkin' Donuts. We're ordering our coffee. I tried to put in for the field trip, Mr. Zider said no. Because you didn't have your ID back. That's right. All right, I'll give you, I don't know, 5, 10 or so minutes. You will need a calculator. Some of these numbers are going to get big. See what you can do for Duncan. Pull it in, no worries. All right, there it is. Okay, I've got all my work up here for you too. Okay, so for the first one, not picking a flavor shot is one of the choices. So there's 7 flavor shots plus the 8th option is not to pick one at all. So that's where the 128 comes from. Same thing for number 2, that 4 at the end, you can pick whipped cream, chocolate, caramel, or none. So there are 4 choices for the topping option. 512. Okay, make sense for those? Okay. All right, number 3. It's a 4-digit passcode. Think about for each digit, how many choices you have. There are 9 choices for each of the 4 digits. So 9 times 9 times 9 times 9 because they can repeat. Yes?
It says 4 different digits.
4, does it say 4 different digits? Oh, shoot. I didn't read it right. That would change my answer. Okay, hold on. If it says different digits, I can pick 9 for the first choice. 9 times 8 times 7 times 6, but you're only still multiplying 4 numbers because 4 digits. Good catch, Ethan. Thank you. It would help if I read it. All right. 3024. There we go. Got it. Okay. And then for the last one, we need all different digits. It's a 9-digit code, so we go all the way down to 1, which is the same. Do you guys remember this symbol, the factorial symbol, little exclamation point? This is in your calculator. If you guys want to find it, it can save you if you've got some big numbers. It's under math. You hit the math button, and then if you go over to the right where it says PROB, that's the probability menu. We're going to use a few things in that menu, but you'll see the factorial symbol there. You also have this symbol on the red calculator, so when we get to like test and quiz and stuff, you'll have that available to you. Okay. All right. Any questions on those two? Okay, on the back. Again, you got to read pretty carefully here. Okay, so the first one, the first 3 spots are letters that can repeat. So 26, 26, 26, or you could say 26 to the 3rd. And the last 6 are digits that cannot repeat. So that's what we have 10, 9, 8, 7, 6, 5. And then I multiply them to get that number. Next one, a 9-digit code where the first 4 spots are letters that cannot repeat. So we start with 26 all the way down to 23. The last 5 are digits that can repeat. So 10 choices for each of those, or you could just say 10 to the 5th. And then I get that number. I just left it in scientific notation. It got pretty big. Last one, 9-digit code. First 5 are letters that can repeat, but can't be vowels. So we take out the 5 vowels. There are 21 choices for the first 5 spots. So I just wrote 21 to the 5th. And the last 4 are even digits that can also repeat. There's 5 even digits. There's 5 odd digits. And there's, thank you, 4 of those. So 5 to the 4th. One thing you might see in Math Excel, how many prime digits are there? Remember what a prime number is? Number that's divisible by 1 in itself. What's the first prime number? 1 is not prime. 2 is the first and only even prime number. So 2, what else is prime? The digits, 0 through 9. 2, 3, 5, and 7. There are 4 prime digits. 5 odd, 5 even. Okay, and then if you're Duncan and you're choosing which one you want to use, so it's less likely to be guessed, you're going to pick the one that has the most possibilities, which is the middle one, and the probability of it being guessed correctly is 1 out of that many choices, which I just left like that. Make the decimal there. Okay, so these can get kind of tricky. You saw I missed something when I read it, so just be really, really careful. Any questions on this? Okay, back to your little paper. Let's finish up the last couple slides on there. Okay. The probability of any event occurring is going to look like this in notation. It's going to say P and then in parentheses E, just as generic for event, but it might say P and then parentheses odd, meaning the probability of rolling an odd or picking an odd digit, or P and then club, you know, the probability of selecting a club out of a deck of cards. So whatever we're calculating the probability of, that's what's in the parentheses there. This isn't on your paper. You might just want to write this in the margin somewhere. The probability of any event occurring is between 0 and 1. Those are our only options. 0 means the event will not happen, and 1, it is certain to happen. And then anywhere in between there, we've got this kind of sliding scale. Okay. The complement of an event is written like this. Okay, it's got a little prime, E prime, we say. And the probability of an event plus the probability of its complement equal 1. Okay, complement means everything except that event. So it either happens, that's the probability of E, or it doesn't happen, and that's the probability of E prime, and together that adds up to 1, all the possible options. If you want to calculate the probability of E prime, you can kind of just manipulate this line here. I can subtract the probability of E to the other side. So if you have the probability of a specific event, let's pretend the probability of an event occurring is like 0.2. Its complement would be 0.8, 1 minus that. That's all we do. And this little picture here kind of shows you the sample space and the two options. It either is E or it's not E. Okay. All right. So next couple problems are relatively quick. They're the 3 types of probability that we could have. The first is the one that you are most familiar with. It is called classical or theoretical probability. Our book uses classical, but theoretical is what you may have heard in the past. It is a formula that says pretty much, what do you want to happen? That's the numerator, divided by how many things can happen. That's the denominator, and that's how we calculate the probability. Typically, we're going to write this as a decimal, but it could be a fraction or a percentage. All right, so let's practice a few. You roll a 6-sided die. Find the probability of rolling a 3. So if I roll a die, how many ways are there to get a 3? 1. And how many possibilities are there to roll total? So 1 out of 6 is the probability, or as a decimal, it'd be 0.167 if I rounded to 3 decimal spaces. Probability of rolling a 7 on a 6-sided die is 0, impossible. Probability of rolling a number less than 5. 4 out of 6, or 2/3, or 0.667. For several problems in this chapter, you're going to need to know about your deck of cards. How many cards are in a deck of cards? 52. And unless it says jokers, we assume the jokers are taken out. Okay? How many of each heart, diamond are suits? We've got how many of each? 4 suits. 13 of each. Okay, so 13 of each suit, 4 suits. How many of each number? Like how many 2s, how many 3s, how many 4s? 4 of each. How many face cards? Do they have a face on them? 12. They do not, no. So Jack, Queen, and King are considered face cards, and so there are 12 of those. Okay, so those words might pop up a little bit. All right, so next event is, what's the probability of selecting a 9 of clubs? If I pick one card. How many 9 of clubs are there in a deck of cards? 1. 1 out of 52. Or 0.019. Selecting a heart, one of our suits. 13 out of 52, bless you, or 1 out of 4, or 0.25. Probability of selecting a diamond, or a heart, or a club, or a spade. 100%, 1. I'm going to pick one of those for sure. Okay. Questions on classical, in theory, theoretical probability. Great. Okay. Next 2 are quick. The next one is called empirical. Empirical is based on an experiment, it's easy to remember, they both start with E's. An experiment's kind of a loose term. It could be based on like observations or survey results, but it's based on some previous data that has been collected in some way, okay? The calculation is still the same. It's what do we want to happen divided by how many there are total. It's just based on previous data, okay? So here we've got a survey. 1,490 adults were surveyed, and they figured out how they read books. They either don't read books, or they read print, or digital, or both. We want to know what's the probability that the next adult surveyed will read only print books, okay? And we're using this previous information. So in this little pie chart, how many read only print books? 578. Out of how many there were total? 1,490, and that's your probability. Okay, so it's calculated the same way as before, just based on some previous information that we know. Okay, so that's empirical. So we have classical, in theory, empirical, based on an experiment, and the third is subjective. Subjective probability is based on an educated guess, intuition, estimate, hunch, okay? So nothing really backing it. We don't have theory backing it. We don't have survey results backing it. Just we think this is what's going to happen, okay? So the next three, we're just labeling what type of probability it is. Is it classical, based on theory, empirical, based on an observation or an experiment, or subjective, based on a hunch? Probability that you will get an A on your next test is 0.9. Is that based on theory? Is it based on an experiment or observations that we're aware of? Not that they told us. So that is an example of subjective. Okay, it's a guess, an estimate. For some of us, a prayer, you know, okay? Probability that a voter chosen at random will be younger than 35 years old is 0.3. So voter data is based on census information, voter registration, right? There's something that is coming from, okay? So what type of probability is that? That's empirical. Okay, the last one, probability of winning a 1,000-ticket raffle. One ticket is 1 out of 1,000. So I buy one raffle ticket, 1,000 are sold. My probability of winning is 1 out of 1,000. What type of probability is that? That's classical. That's based on theory. Okay. Last question for today. Using the frequency distribution chart to the right, find the probability of selecting a social networking site user who is not 23 to 35 years old. Okay, there's two ways to do this problem. We're going to do it emphasizing this word. Okay, the word not means you are using a complement. It's everything except the 23 to 35-year-olds. So how we can do it, the simplest way to do it, is to figure out what's the probability of selecting a 23 to 35-year-old, which here there are 312 of them, and they've nicely totaled them up at the bottom for us. The sum of all the frequencies is 975. I want everybody except them. So this is where we can use our little 1 minus and get our answer. 0.32 is what you get if you do 312 over 975. So the probability is 0.68. You can get that same answer by adding up all the other categories and dividing by 975. But depending how many categories we have in problems like this can be much simpler if you see that word and use that fact, okay? All right, tomorrow we're going to do a little activity with Hershey's Kisses to learn about the law of large numbers, and then we're going to start section 3.2. This homework assignment, guys, 3.1 is due tomorrow night. Next homework is due tomorrow night. The lesson tomorrow?